let's talk about the synapse. All right. So we know that synapses, right? Synapses they're called, right? Are sites between adjacent neurons, right? So they tend to be around 20 to around, let's say, 50 nanometers wide. All right. So they're really, really tiny space between them, right? And this gap, right, between synapses are called the synaptic cleft. So let's look at something like this. Right? So let's call this our pre-synaptic neuron, and this is our post-synaptic neuron, right? So here we have a gap between them, right? And this gap, right, is called the synaptic cleft. Right, so it's usually referred to as the synaptic cleft, right? So remember, it's between an axon and the dendrite. Please remember that, axon and a dendrite. So we're looking at this, right? So action potentials can undergo solitary conduction, right? Meaning that they can't leap across a synaptic cleft. Right. So what we notice is that if action potentials are to move from one to the other, they have to change their signals from electrical to chemical, then to electrical. Right? And these are usually helped out by neurotransmitters. Right? The most notable neurotransmitters that we have that we can talk about would probably be acetylcholine. Or as I would just write in the future, ACH, like that. Right? And there's also some like GABA, right? GABA, right? Which are important. Or we're just gonna be focusing on the content that's really necessary, right, for K-Biology Unit 2 so far. Right? So we have this information here. Now, how does action potentials cross the synapse? Right? So firstly, let's just draw a huge diagram of the synapse. Right? It's not my best work. But let's just draw a huge diagram of the synapse and I'll work with that. Alright? So this is the presynaptic neuron. So the first thing that has to happen, why did I create a plus? The first thing that has to happen is that the action potential reaches the axon terminals, right? So for the synapse, right, for the synapse. So the action potential arrives from the axon. So we know it's traveling in a wave through the axon, right? Upon arrival, we're gonna see, right, that the action potential allows the opening of potassium. The action potential arrives, right? Let's start there. Channels open to allow the sodium and calcium ions to really move through and enter the bulb, right? So remember, this is like a bulb-like shape. So this is what we call like a bulb per se. Right? So we're gonna allow calcium. Alright, so let's have a look at something that would allow the calcium to come in. like a channel, right? And this would allow calcium ions to come rushing in, right? So the calcium ions come rushing in, and this stimulates the formation and the movement of vesicles, right? So it causes, so the potassium ions, right, causes the movement of, let's say that this is a vesicle, right? And remember that this vesicle has acetylcholine in it, right? It stimulates the movement of vesicles towards the cleft, right? So let me provide a little bit more room. So it stimulates the movement of the vesicles towards the cleft. Let me draw that again. So the ion comes in and it stimulates the movement of the vesicles with acetylcholine as the receptors, and it goes towards the cleft. Right? So keep that in mind. Alright, so stimulates the movement of vesicles towards the cleft. Right, towards the cleft. Right, so we have that there. And this usually has acetylcholine being released through exocytosis. Right, so it's going to have a release through exocytosis. So we're going to have exocytosis happening, and the acetylcholine is going to be released. Now, the third step really, we're gonna see that there are channels, right, for sodium. So what will happen is that the acetylcholine will actually attach to the sodium channel and allow for sodium to enter the postsynaptic neurons, right? So this is a ligand-gated channel. Ligand-gated channel. So it's ligand-gated. So if we could remember from chemistry, ligands form these different complexes, right? So it has to form a complex with acetylcholine first, right, to activate it to cause sodium ions to start moving in, right? And this will now depolarize the postsynaptic membrane, right? So this is what causes depolarization. Right? This influx of sodium ions, right, will actually cause the next active potential, or sorry, action potential. The next action potential. So the influx of sodium ions will depolarize it and cause the next action potential to go through there, right? So that's what's happening. Let's say that's step 3, right? Step 4 now, we will see that there's an enzyme in the gap here, in the synaptic gap, right? And it's called acetylcholinesterase, right? So an enzyme, acetylcholinesterase, right? So acetylcholinesterase is gonna be there. It looks really weird. So acetylcholinesterase. I'm gonna draw it a little bit better. Let me go back. It's a bit weird. Alright, so let me just fix that real quick. So we're gonna have acetylcholinesterase, and this would be in step 4. So let me just draw acetylcholinesterase here. Acetylcholinesterase. Right, so that would be the enzyme that is active here. So there is going to be that enzyme here. So that acetylcholinesterase is going to be the enzyme here. And it causes the breakdown of acetylcholine back into acetates. The A is the acetate. Acetate. And the CH is the choline. That's why it's acetylcholine. So it facilitates the breakdown back into acetate and acetylcholine. Right? So what's gonna happen here at 5 now, at step 5, we're gonna, well, this is step 4. Alright? At step 5 now, we're gonna see the choline receptors come in. Right? So the choline receptors are gonna come in and they're going to reform acetylcholine here. Right? But this really happens within the mitochondria. So remember Krebs cycle? Remember Krebs cycle? The link reaction? We're gonna have the coenzyme A. CoA is gonna go into the mitochondria here. And that's gonna create acetyl-CoA. Right? We're gonna create acetyl-CoA. Right? So that's what's gonna happen here, and it's gonna create this complex. Right? And that will happen over and over and over again. Right? So this really happens in the presynaptic bulb. Now, I'm going to be dividing this up into different sections now. Right? I should probably have divided up into different sections. So let me divide it up into different sections to properly go through it with you. So step 1, the action potential reaches the synapse. Right? So let's say presynaptic bulb, postsynaptic bulb, action potential reaches a synapse. Right? In step 2, right, what we're gonna have is that within the presynaptic neuron, right, we're gonna have acetyl-CoA through the process of endocytosis, right, it's gonna leave, right? So acetyl-CoA going through in 2, right? And this is being caused by the gated calcium channels 2+, right? So forcing calcium 2+ air, and calcium 2+ will stimulate the movement of acetylcholine throughout the presynaptic bulb and causes acetylcholine to be removed through exocytosis. Right? Step 3, all we're gonna have here for step 3, acetylcholine is now present within the area. It will actually approach the postsynaptic neuron, right, on its sodium channel. So it will attach with sodium channel on this ligand gated channel and causes sodium ions to enter. When sodium ions enter, they tend to depolarize the cell, and it causes this next action potential, right? So causes the next action potential. All right, so that's working so far. That's step 3 right there. For step 4, let's breaking it up. For step 4, we're gonna have within the bulb, well, not within the bulb, within the presynaptic, well, within the gap, right? We're gonna have acetylcholinesterase, and this is gonna break down acetylcholine into its acetate, right, and its choline. Well, the acetylcholine that doesn't respond, or that doesn't react. So well, after it reacts, it's gonna break down. Yeah, so it doesn't keep on, activating. right? So remember that the acetylcholine has to bond here for the polarization to happen and for the action potential to fire, right? But if there's not enough acetylcholinesterase, then we're gonna have a reaction keep on happening on the ligand-gated channel, and we're gonna end up with diseases such as Parkinson's, right? So like Parkinson's disease. And here we have 4 there. That's 4. At 5 now, we're gonna now see that the choline, right? So the choline re-enters. So choline re-enters the presynaptic bulb, right? And it combines with acetate to create acetylcholine again, right? But we have to know where this acetate comes from. This acetate comes from the general reaction in the mitochondria, or in the mitochondrion, right? So remember this reaction. Coenzyme A goes through the mitochondria, you get acetyl-CoA, right? The acetyl-CoA is technically the acetate that we have going to the choline to create the to regenerate the acetylcholine, right? So those are all the steps, right? I know the first part was a bit tricky, right? Going through all of these steps here on one page, right? But I'll try to make sure that this doesn't really happen again, right? So that is really looking at the synapse, right? So that's that.